So today is the last section of chapter 2.3, of chapter 2. Remember, chapter 2 is about this thing which is called, which is a number which we calculate for which we can calculate for every square matrix. And this number tells us if the matrix is invertible, if the number is non-zero, and if the number is 0, it is not invertible. We have not had this result, but keep in mind that was the goal of, for us at least, for the determinant. So 2.3 is now more properties of the determinant. And we finished the section which is something called is Cramer's rule. I don't really know how to pronounce his name. I think he's from Switzerland. Or, yeah, so it can be French or German, or I don't know how this guy is pronounced. So before we start, we look back at one thing which we already learned about the determinant. If you have A in n by n matrix, so A can be written as a sequence of rows. So let's say here's row 1 down to row n. And now the question is, what is the determinant of alpha times A, where alpha is a number? Then how do we multiply a matrix by a number? We have to distribute alpha to every entry. So in this way of writing it, it means I have to distribute alpha to every row. So this would be the determinant of the matrix, where the first row is now alpha A1, the second row is alpha A2, down up to alpha AN. Okay, and yesterday we learned if we have a row with a number, the number we can actually factor. So I can take this alpha and take it out. So now this is just A1 because I factored, and all the rest still have the alpha in it. So now I can do the same thing with the alpha in the second row. So I take it out. So we get alpha square determinant of the matrix, where now the first row is A1, the second row is A2, but in the third row there's still an alpha. So, okay, and I don't like to continue now step by step, but now I would take the alpha out in the third row and just continue, take out one alpha after the other. So if I do this and we have n rows, at the end we end up with alpha to the power of n, determinant of first row is now A1, second row is now A2, up to last row is AN. And it turns out we are back to our original matrix A. So this is alpha to the power of n det A. Okay, so now you can ask why this long calculation. I mean, first for sure that works like this. So what it means, determinant of alpha times a matrix is alpha to the power of n times the determinant of the matrix. So this is a sign, or essentially it shows that the determinant function is not linear, because linear would mean I can just take out the alpha. So it turns out, so the det function is not linear. So, and that already indicates that maybe this one, if you take two matrices, it's also not the same as det A plus det B. And it turns out, in general, this is true. Determinant of A and B is not equal to determinant A plus determinant B. Sometimes it's true, but that's just by luck. And you would be able to show this by just doing an example. You can just take the identity matrix and split it in two parts, and this is 0, and this is 1. So So it's very easy to show. So both of these, this is a nice rule. This just shows something is not true. Both of them indicate that the determinant is not a linear function, but it's actually linear in each vector, also in each row vector and each column vector. And that is actually what the next theorem tells us. So the theorem says the following. I start with calling the matrix C, so I can make C as equal to A plus B. So that's why this time we start with C. So C, n times n matrix. And so C again, I formulate everything for rows, but it's actually the same for columns. No, it's just out of convenience, I write rows here. So C is a sequence of columns. And now I look specifically at one row, Ci. So this is row I. And I can be any row, can be the first, second, or nth, it doesn't matter. I just say one row I take now at special. And the thing is, this one row I write as a sum of two row vectors. So Ci is equal to Ai plus Bi. And these must also be row vectors of the same length. So maybe just to make sure, I write sum of row vectors. And now I make two other matrices, a matrix A and a matrix B, which is actually totally the same, just at position Ci. For the matrix A, there's Ai, and for the matrix B, instead of Ci, there's Bi. So then define the matrix A, absolutely the same as the matrix C, but in row I, there's not Ci, there's just the Ai, and everything else is C again. And similar with the matrix B, everything is the same as the matrix C, but in row I, there's just a Bi. And then the rest is again C's. And then, so just one row, you split into two rows. And then it turns out that the determinant of C is equal to the determinant of A plus determinant of B. So if you split one row and make it two matrices where everything else stays the same, then you actually can break the determinant apart into two determinants. And again, this is very easy to see according to the definition when we yesterday had the row and column expansion. If you think about the column expansion, and then you expand with respect to row I, and there's always Ai plus Bi, you just distribute. So it turns out this is very easy to show. So I don't even go into the proof. It just would be writing down the row expansion with respect to row I. So this is kind of easy to see. And I just like to show you what this means. So meaning is the following. For example, if I have the determinant of a matrix 1, 7, 5, 2, 0, 3, 1, 5, 6. And now I grab one of the rows, and in my example, I just grabbed this row and write 1, 5, 6 as a row vector is equal to, I did it in this way, 1, 0, 6 plus 0, 5, 0. So in my theorem here, so this would be C3, this is A3, and this is B3. So one of the rows I split into two rows. And it turns out what this theorem now tells you, this determinant is the same as the determinant of, now you take first this part, and everything else stays the same. Here the C's here are the same, so it's 1, 7, 5, 2, 0, 3, plus the determinant of, again, top stays the same. But here now we get the second vector 0, 5, 0. So you see I split this row into 2 rows and all the rest is the same. And it turns out that is actually correct. This is what this theorem, also I forgot the number, this is 2.31 in your book. So this is what theorem 2.31 tells you. So if you ever need to do this, that you have a matrix and you like to split one row or one column, that you can do. But all the rest, you need to copy. So this kind of behavior makes the determinant a function, which I said is not linear, but we call it multilinear. So determinant is a multilinear function.
Professor, can you go over on how you split the rows?
So it's linear with respect to every row or every column, but not linear with respect to the matrix A. So this is what this and this here shows you. Okay, so after this, so this is just essentially telling you, sometimes you have to be careful with determinant. They're not linear, but they're linear in every argument. Okay, now I like to finally come to the to prepare for the most important part about the determinant is that the determinant, if it's not 0, the matrix has an inverse. Remember, that was kind of the original motivation, which I also mentioned at the beginning of today's class. Now we go into, okay, how do we do this? How do we see this now? And again, it turns out we have prepared all the groundwork. We just have to put results together. So I go to the next page. So hopefully I have, when I do this, at the end, I have everything on one page so I can refer to all the results I need.
Professor?
So yesterday, we already talked about the 3 elementary matrices.
Professor, can you hear us? Hello?
I don't know if you can hear us.
I don't think
These were 3 types.
I don't think you can at all.
MI alpha means multiply row I by alpha. SIJ means switch row I and J. And AI alpha J means add alpha times row J to row I. And sorry, I just saw accidentally someone raised his hand. Any questions? Sorry.
Professor, you can't hear us. Can you hear us? Hello? I texted in the chat.
Did someone had a question? I saw something.
Hopefully he can look in the chat.
Okay, so please let me know if there's a question. Otherwise, I continue. Or yeah. So. And now we also learned yesterday what happens if you multiply one row with a number in the matrix, what happens if you switch 2 rows, and what happens if you add 1 row times a number to another row. Important here and here is that I and J are not the same. Yvonne, sorry?
Can you hear me, Professor? Hello?
Oh. Okay, sorry. Huh.
Can you hear us now, Professor?
So let's see what I have here. Sorry. Okay, can someone say something?
Can you hear us now, Professor?
Okay, now I hear you on my headphones. One moment. Oh, okay, sorry. That is kind of funny. So how do I do this now? I need to put, yeah. Let's try this. Can someone just try again?
Can you hear us, Professor? Hello?
Now it works. Sorry. I have 3 microphones, speakers on my, and yeah. Okay, sorry. Okay.
People were asking you some questions about the previous page, but
okay, just one moment, I'll bring it back. Yeah, funny. Okay, sorry.
Yeah, I have a question. Okay, go ahead. Oh, sorry. Can you explain over again how did you split the matches? Like, how did you get the 106 and 050?
Again, it's just an example. Also, I can split it in any way I like. Just these two vectors together must give me this vector, no? If you add this, 1 plus 0 is 1, 0 plus 5 is 5, 6 plus 0 is 6.
Got it.
So I just take the vector and split it. And this is just an example. So there's no deep reason why I split it. It's just an example, no?
Okay, thank you.
You can split it in any way you like, actually, no? Also, there are infinitely many possibilities.
Okay, thank you.
Yeah, also, yeah.
Professor, what does it say? Determinant is a multiple? Is that what it says?
No, it's multi. Sorry?
Okay, multi. Okay.
Yeah. So there are functions which we call multilinear, and I don't know if you have in any other class seen anything like a multilinear function, but determinants are kind of the prime example of what we call multilinear functions. If you have been, I'm not sure what kind of your background you have. If you're more like physics or engineering, there's something called, they call it tensors. And tensors are multilinear functions also, but I'm not sure. I mean, you might never heard these words. Yeah, but this is an example of what we call multilinear, and it means the determinant is linear, not overall, but with respect to every column or row. That's just what it means, no?
Got it. Thank you for clarifying that.
Yeah, and thank you for letting me know that I didn't hear you. Actually, that was yeah. Sorry, no intention.
What is that word up at the top above the determinant?
Here?
Very up at the very top.
Oh, yeah. Essentially, it's the meaning. It says meaning of this theorem. No,
okay,
I just try to
Thank
make it. Okay, yeah. I'm sorry.
No, it's no problem. You don't have to rewrite it. I couldn't read it.
Okay, so meaning, or you can say it's an explanation or an example for this theorem. No.
I think we're all good. Thanks, Professor.
Okay. Yeah, sorry. I don't know how this happened, but I had the wrong speaker for Zoom on. Okay.